Hi there, welcome to the session on change data capture. I'm Prasad Radhakrishnan. I'm from the product team. And with me, I have Suranjan Kumar.
This is Ranjan Kumar from database engineering team. We have worked on the change data capture, and today along with Prasad, I'll be talking about its implementation in YugabyteDB.
Awesome. So change data, let's quickly touch on scope of the problem. So what is CDC? In databases, change data capture is a set of software design patterns used to determine and track the data that has changed so that action can be taken using the change data. This is a classic Wikipedia definition of CDC. The key words to highlight here is going to be track, change, and action. So we want to be able to track what has changed so we can enable any downstream action based on that, right? Let's expand on that a little bit more. So let's take a very simple example. There is a table with customer ID, first name, last name, email, and update timestamp. So the email changed from g.doe to john.doe, something like that. Now from here, as soon as the change happens, we want to call an external API to validate if it is an email address, number one. Number two, maybe we want to update some marketing database and systems, and then also send this change over to a data lake so it also stays updated. So as you can see in this simple example, based on a change, there are downstream actions to be taken. So there is change, there is tracking the change, and there is notification. So this, in some sense, is the scope of the CDC problem at a very high level, right? So let's see, now this is not new. It has been around for several years, decades. So people have been handling change data. So what were some of the popular solutions, right? So one, as you can see in this example, I had kept a column there called update timestamp. So you can track using timestamps on rows. So this is assuming that the table was designed right and the app knows that every time something is changing in that record, it's going to flip or update the update timestamp field. So you could simply do select star from this table where update timestamp is greater than whatever is the previous value, and then get the changes, and then you can go on and do whatever you have to do based on that. So here the great trust is placed on the update timestamp field, assuming the app updates it religiously. And it's a very old method or technique. It's been used before some of more sophisticated solutions fell in place. Now another approach is by doing a table diff. Sometimes when building large warehouses, people take a full snapshot of the database, as in yesterday's snapshot. Then you get to take yesterday's table, today's table, do a delta by using a minus or similar operation and see what has changed. And then you get what has new records, updated records, deleted records, and based on that, again, you can go do something. So that's another approach. Then you could use triggers as well, as in per table, you can have some triggers created, and as soon as something happens, then the trigger is triggered. And based on that, again, it's not foolproof. And again, this is also something people have used in the past. Then came this, whole idea of using the transaction logs. Now, this doesn't put any additional stress on the database because you are basically consuming the logs. And if there is a way for you to interpret the logs, then you know what are all the changes that has happened. And then you can go process it and update any other downstream databases that are out there. Now, if the database technology happens to be something proprietary like Oracle or SQL Server, then you will have to end up buying a CDC tool, and usually that's going to be expensive. So there is that. However, this has proven to be an approach, a good approach, and it has worked really well. So kind of approved. So most any solution, CDC solution, is based on transaction logs and how we can use that to apply the changes downstream. Right. So that brings us to understanding a little bit about transaction logs and what's out there. So the two popular ones that is worthy of discussing is going to be B-tree and LSM. Okay. So why these two are thing to focus on, because among the popular databases out there, they are either using B-tree or LSM, and some actually use a combination, or in one mode it's B-tree, another mode LSM. But if you take the popular ones like Oracle, SQL Server, DB2, Postgres, and even MySQL, they use B-tree. So B-tree predates LSM in terms of popular usage. A lot of the older database technologies, as you can see, they use B-tree. It works really well for non-distributed databases, right? B-tree files tend to grow wider and shallow. So it's better optimized for reads. Random writes, for instance, updates that are not in any particular order and operations like that would relatively have poorer performance. Now, in the 2000s, as data explosion happened, then there was a need to find something better than B-tree, and LSM, then was born, and not born, it became got more mainstream usage, and most of the modern databases now tend to look at LSM or use LSM, and LSM stands for log structured merge tree, tongue twister sometimes. No, the primary reason behind LSM success is that it can do fast sequential writes as opposed to slow random writes when it comes to B-tree. Like Cassandra, HBase, and even Yugabyte use LSM-based database engines. And when it comes to Yugabyte, we use an optimized version of RocksDB, which is also LSM-based, and that's our storage engine. Now, how exactly is LSM used? Again, from a 10,000 feet level, let's take a very simple example. In Yugabyte, you create a user table. Now that gets sharded. A shard in Yugabyte is called tablet. So you have multiple tablets per table, and therefore several tablets in a Yugabyte cluster. And each tablet gets its own write-ahead log file. Now, this write-ahead log file is LSM-based. The wall is not in memory. It's disk persisted. Each wall, this is important to understand because it is very relevant when we walk into the CDC implementation. Each wall preserves the order in which transactions happen. And it also stores some very useful information like the hybrid timestamp, op ID, and additional metadata about the transaction is also preserved in the wall file.
Once we know about the structure of wall file and the way data is stored in YugabyteDB, let's talk about CDC in YugabyteDB and how it takes advantage of that. Right. So this is just the previous structure where we saw that the table is basically distributed across multiple tablets, which is nothing but multiple shards. Each tablet has its own wall, which is nothing but a persisted structure where we, as Prasad mentioned, we store all the metadata as well as the data that gets stored in YugabyteDB. Now, from the CDC perspective, we want to consume this data, right? And we also want to build a highly scalable and distributed solution where just like YugabyteDB, it is highly available as well as linearly scalable. As we know, can we go back? Yeah. As we know that YugabyteDB, even if a node goes down or when you add a couple of nodes, its throughput will increase, its storage capacity will increase. And the CDC solution that we went for was to take into account these features of YugabyteDB so that this can also scale. Yeah, next slide. To do that, we took advantage of one of the framework called Kafka Connect, which itself is a distributed cluster. Kafka Connect will have a coordinator node, and then there will be worker nodes, similar to YugabyteDB cluster, which has its master nodes, and there are T-server nodes. And we know that Kafka Connect cluster works with Kafka cluster, which itself is again a distributed scalable solutions for distributed queue-based architecture. And the Kafka Connect YugabyteDB connector that we have written, it is based on the CDC service API that we exposed from YugabyteDB. As we can see, it's a scalable solution in the sense that we can launch as many tasks as we want. Each task can independently go and pick the changes for each of the tablet, depending on how do we want to group the set of tablets for, and these tasks are completely independent to each other. The high availability can we go back? Yeah. The high availability comes even if, for example, a worker node goes down, your task can get rescheduled to another worker node which are available in the system. Going with Kafka has given us advantage in terms of syncs. It has a very the ecosystem of Kafka has lot many syncs already available. So once your data is in Kafka, the solutions to get the data out from Kafka to S3 or SDFS or Snowflake has multiple solutions already available. Yeah. If you want to understand how does YugabyteDB component and Kafka components map to each other, and how do the concepts at the conceptual level are similar. A table in YugabyteDB could be as simple as a topic in Kafka, although there are ways in which you can combine multiple tables to a topic to take care of some of the use cases. A tablet, which is nothing but a sardine of a table, can be a simple partition of a topic. Throughput, as you increase the number of nodes that I talked about in YugabyteDB, your throughput may increase. Right. In that case, you also would like to increase the performance of your CDC so that you are able to fetch data as and when your write operations increase. So that is controlled by the number of tasks that you want to launch. In some cases, you may also want to increase the number of worker nodes, just in case the total number of the capacity of the Kafka Connect cluster is not able to fetch data at the rate at which write operation is taking place in YugabyteDB. And YugabyteDB cluster is similar to, because it's a distributed cluster, it is almost similar to Kafka and Kafka Connect cluster outside.
Very cool. Very cool. Just to expand, a little bit on what Suranjan, walked us through. Let's take this, simple example. I have, YugabyteDB's, and we are, kind of having an isolated sliced view of, let's say, a table called order details, and it has got, 5 tablets as an example, right? So how does this work? You have the Yugabyte cluster, which is source. You have Kafka Connect cluster, which is bringing, scalable consumers to consume change data, and then it is and then it will be writing to, Kafka cluster, which happens to be the first point of sync, where, there is a Kafka topic with a bunch of partitions, right? So to sort of, so you have this Yugabyte to Kafka Connect, and then there is Kafka Connect to Kafka cluster. So splitting this into, further 2 different views, let's look at the first half. So here you have order details table with 5 tablets. So first, a stream ID is created, which is something you do at the very beginning, and it is 1 per database. And then you get to include or exclude, for instance, if the database has hundreds of tables, but you are interested to consume, CDC from just a handful, then that's that, right? You could, simply say these are the tables from which you want to consume change data. And then, checkpoint is the whole notion of Yugabyte keeping track of where the consumers are and how much of change data they have consumed. Then there is batch size that is configurable on the Yugabyte side. And then there is polling frequency that you get to control on the consumer side, which is Kafka Connect. And then a task, which, Suranjan mentioned, is, actually a consumer. And a task can consume from multiple tablets. It need not be one-on-one, and usually it's not one-on-one. And this entire CDC implementation guarantees at least once delivery. Obviously, Kafka Connect brings high availability on the consumer side. An example there would be, let's say if a task fails, Kafka Connect takes care of, spinning it in a different node, and then, it knows how to connect and consume from where it left off.
If you look at the lower part, right? So every task that consumes the data from YugabyteDB cluster, it writes to Kafka. And as I talked about earlier, each table is nothing but mapped to by default, it is mapped to a topic. However, you can also configure it to map to multiple tables can be mapped to a single topic. But task to Kafka partition, for example, this need not be one-to-one mapping. As and when, the way you want to basically scale your Kafka cluster, you can do that. You can have a single partition if you want. You can have multiple partitions for a topic. You can independently that all three components, the YugabyteDB, the Kafka Connect cluster, and Kafka clusters, all three components can be independently scaled, and you can scale the tasks as and when required, and you can scale the storage of YugabyteDB or the Kafka as well. In one of the advantage of Yugabyte CDC as opposed to other connectors is that we maintain our checkpoint ourselves. Because YugabyteDB is a database, we ourselves provide high availability and scalability. For each of the tablet and stream, we maintain these checkpoints as opposed to other connectors that store that in Kafka. We also maintain, we have in our wall structure, something called op ID, which is nothing but log sequence number. And that is used to maintain this checkpoint information that, okay, from this point, the data has been consumed. As Prasad said, we guarantee at least once delivery. Not only that, we also ensure that all the changes that you receive are in the order that were changed in that particular tablet. So in a particular tablet, all the changes that happens in a particular order, client will receive all the changes in the same order.
Awesome. So with that, now we will switch over to the demo mode.
Okay, for the demo, I'll just explain the setup a bit. As we see, there are like multiple components. One is YugabyteDB cluster. Then we have this Kafka Connect cluster. We have Kafka clusters, and this is the end user application, which we can say the Postgres or simple Kafka consumer, web UI consumer. A user would be doing some operations mimicking applications in YugabyteDB, one of the table. Kafka Connect will deploy the our CDC connector in this Kafka Connect cluster, which eventually go and pull this data from the particular table and push it to Kafka. From Kafka, we'll deploy a sink, which will push this data from Kafka to Postgres. We'll also analyze what are the messages that are in Kafka using the web UI. Before going to the setup, let me explain a bit about two commands that a user has to execute. One is this create change data stream. This is a YB admin tool that YugabyteDB provides, and this command gets executed in YugabyteDB cluster, which as an input, it takes the name of the database. The output of this command is the stream ID, which is a UUID. This stream ID needs to be fed into your config of the CDC connector. So as you can see, this is the config of the CDC connector. As we talked about in the scalability aspects, you can specify how many tasks you want to run. This is the main class of the connector. And then we have, we support SSL as well as user authentication. So those details, which user is going to, has the permission to basically pull the data out of this. Then we have a snapshot mode, which can be never initial if you want to take the initial snapshot. And this is the stream ID, which the ID that you just created before. The table include list basically specifies which all table you want to stream the data from. So in our demo, we will be modifying this table employee, which the CDC connector will pull the data and push it to Kafka. Okay, now let's go to our demo. This is a YSQL client, which is already connected to the YugabyteDB cluster. As you can see, there is one table called employee. Currently, there is nothing in this table. The table is empty. I'll try to, and this is the Postgres instance that has been running. I'll also see if there is anything present in this table. As we can see, both the tables are empty. I'll try to insert one row in the table, as you have seen, and I'll try to see if the sink has received the same row or not. As you can see, the same row has been received in the sink. Now let's see what has happened in this case. The moment we did this operation, this went into the wall of the this table of one of the tablet. The YugabyteDB connector pulled the changes from the wall, pushed it to Kafka. From the Kafka, the one sync, JDBC sync was running, which picked that change and pushed it to Postgres. Now let's see what change is there in the Kafka. So I have a UI already, consumer UI already running, which is connected to the Kafka cluster. As you can see, the Kafka topic, public.employee, which, as I mentioned earlier, that there is one-to-one mapping by default between a table in YugabyteDB and the topic of Kafka. If I refresh it, you can see that there is one message in this topic. Now let's look at the message. As you can see, this is the message structure. I would be mostly interested in this payload. As you can see in this payload, the before image is null. However, in after image, you can see the ID, first name, last name, and department ID. All these have been populated with the value that we inserted into the table. Now, once this message is in Kafka, multiple applications can consume it from the Kafka. I will just try to do more operations just to showcase the multiple operations that can be, that are basically propagated from Yugabyte to Postgres. So I'll just change the last name from K to Kumar for this ID, and just try to see if that change has been reflected. So as you can see earlier, the last name was K, then it became Kumar. I'll again do the delete. And it should be reflected in the Postgres. So as you have seen, all the different operations that gets executed in YugabyteDB gets immediately reflected in Kafka, as well as any end user application that it is consuming the data from Kafka. That's it is the demo. Thank you.
Nice, short and sweet demo. Thanks, Ranjan. I think now we are ready for Q&A.